Lecture 4, Aggregate Planning, Part 4, the last part of this chapter. So in this part, we're going to have a linear programming model for the aggregate planning problem. So to do so, at first we need to define the parameters in order to formulate the model. So CH here will be the cost of hiring of one worker, CF the cost of firing of one worker, CI will be the cost of holding one unit of stock for one period. CR will be the cost of production per unit in regular time, and CO will be the cost of production per unit in overtime. And CU here will be the idle cost per unit of production. So here we are going to formulate the idle time cost of workers in terms of the units. This means that if they are not idle, how many items they can produce in that time. So yeah, by that approach, we can obtain the cost of being idle for the workers. Okay, and CS here, the cost of subcontracting one unit of production. NT will be the number of production days or working days in period T. K is the number of aggregate units. As you remember, we obtained this in our example. So it's the number of aggregate units produced by one worker in one day or man day. I0 here is the initial inventory at the end of the horizon. W0 is the initial workforce at the beginning of, oh sorry, I0 is not the end. I0 is the initial inventory in the beginning of the planning horizon, and also same for W0, the initial workforce. And DT is the forecast of demand in period T. Okay, so here we can define all these parameters as for example, for CH as CHT. I mean, here we are assuming that all these costs are the same constant over the month, but if it's not, we can have individual costs for each month. Okay, so in order to formulate the problem in terms of a linear programming model, we need to define the decision variables as well. So here are the decision variables, WT workforce level in period T. So we are going to obtain these variables in our linear programming model. Okay, and PT will be production level in period T, IT inventory level, HT the number of hirings in period T, FT the number of firings, OT overtime production in units, UT worker idle time in units, and ST number of units subcontracted from outside supplier. Okay, so now let's see how can we formulate the overtime and idle time variables. So the number of units produced by one worker in period T will be K times NT, right? So K is the aggregate unit produced by one worker per day, and if we multiply this by NT, the work days in period T, then that will be the number of units produced by one worker in period T. And then if we multiply this by WT, it will be the number of total units can be produced by the entire workforce in period T. So this is our availability, right? This is our possibility. And so if now PT, I mean production level at time T, this is what it should be. Okay, so if PT be greater than our possibility, this means that we need to go to overtime, right? Or subcontracting, one of these two. Here we're assuming that we're going to have overtime, so overtime will be PT minus K times NT times WT. But if PT is less than K NT WT, this means that the amount that we need to have in that month is less than our availability. So here we'll have idle time, right? So UT will be this, KNTWT minus PT, okay? So now we can formulate the constraints of the model. So here we do have these constraints in addition to the non-negative constraints. So the first one is the conservation of workforce constraint. So WT, the number of workforce at time T, I mean month T, should be equal to the number of workforce in the previous month plus the number of hirings in this month and minus the number of firings in this month, right? And same for the inventory. So the conservation of units constraints. So inventory at the end of month T will be equal to inventory at the end of the previous month plus the total production of this month plus if we do have subcontracting. So the production in our company and subcontract will be the total input to our let's say company plus the previous month inventory. So if we subtract the DT from this total input, then it will be the end month inventory at period T, at month T, right? And for the constraints relating production level to workforce level, here it is. So PT to production should be equal to KNTWT. This is our total possibility, right? So if we need to have OT, overtime, or maybe idle time. So yeah, PT will be KNTWT plus OT minus UT, okay? So now we can build our linear programming model. Here is the objective function. We want to minimize the total cost over the planning horizon. So we just need to multiply the costs by the variables and then add up all the cost terms here. So this will be our total cost, and we want to minimize this. And here we do have the constraints. So yeah. And also the non-negativity constraints here, okay? So for our example that we solve by the two strategies of, two extreme strategies, level and chase strategy. So if we consider those data here, this will be our linear program model for that one. So yeah, here these are the cost parameters, and we are multiplying these cost parameters by their related decision variables. And here we do have the constraints like we had in our previous slides. And these are the initial values. I0 here is 200, I8, inventory at the end of month 8 should be 100. This is a constraint actually here, and W0 is 40, okay? So now if we solve this linear programming model in Excel, for example, or in other applications like GAMS that we can use for solving linear programming models, we can obtain the optimal solution for our example, okay? Now here is the solution that we have obtained by solving that linear programming model. And so yeah, see here over the month, here we do have the number of workers we need to have in the month. So as you see here, we have three changes. At first, we need to hire 6 new workers, and then in April we need to fire 10 of them. It will be 36 for 2 months, and then we will hire 14 in June, and then fire 14 in June, and then it will be constant over the last 3 months, okay? Yeah, as you see here, it's a case between the chase and the constant level of workforce strategy, okay? And here we do have the production obtained by the linear programming model, PT, so the cumulative one, and end month inventory. So the total here, the value of objective function, which is the total cost, is 467,450, which, as you see here, it's much less than the total cost of chase strategy and also the level strategy. So here, this is our optimal solution. Okay. When we have a linear programming model, as it's based on continuous variables, so we may have fractional values for our variables. So if we run off all the fractional values, then the solution may be infeasible. So here we do have a conservative rounding. We can round WT, the number of workers into that period T, to the next larger integer. And then by having that, we can easily obtain HD, FD, and PT. So yeah, the only thing that we can actually round it up is the number of workers. Okay. And here are extensions that we can have for our linear programming model. If we want to deal with uncertainty, then we may decide to have buffer inventory, right? So in order to have that in our model, we just need to have this kind of constraint. The inventory level at the end of each month should be greater than or equal to the buffer limit. Okay, and if we have a capacity constraint here, then we can have this constraint PT, production at time t should be less than or equal to our capacity. And also we can consider the excess or shortage inventory in our model by this. So IT will be equal to IT plus minus IT negative. So here the IT plus will be the excess inventory, and IT negative will be the shortage in our inventory. So in our model, we need to have two types of costs here. So the holding cost will be multiplied by the I plus, and the shortage cost or penalty cost will be multiplied by the negative IT. So yeah, we can actually extend our linear programming model by including these three constraints. Okay, so we are done on this chapter. Just to wrap up this chapter, here we are considering the aggregate planning. We have three strategies: level, chase, and mixed. So as you saw in our example, the two cases of level and chase strategies are the two extremes, and none of these two is optimal, but we may obtain an optimal solution by having a mixed strategy. And to do so, we developed a linear programming model here. And as you saw for our example, if we solve that linear programming model, we can obtain the optimal solution, which minimizes the total cost for the company. Okay, and that's it. Thank you.